In this video, we'll continue talking about molecular polarity. And so we have another example here. This is boron trifluoride, and you can see that they are arranged in a trigonal planar shape. So it's a triangle. And if I show the bond dipoles, you can see that the fluorine is much more electronegative than the boron, so you'll get these dipoles. Now, if we look for the molecular dipole, that is, does this have a positive and a negative end? And I'll show you the partial charges first, right? Positive, negative, negative, negative. But for the whole molecule, we don't see anything. And again, this is because there's a symmetry here. This is like an equilateral triangle, and each of these kind of arrows will kind of exactly cancel the other one out, which is also to say that because each fluorine has the same partial negative charge, no matter what direction we come, we say that there's no positive or negative end. Now let's look at how about this guy? Okay, so this is fluoromethane, and you'll see that, okay, within the carbon and hydrogens, the hydrogens will be the slightly positives, and the carbon will be slightly negative. But then between the carbon and the fluorine, the carbon would be slightly positive, and the fluorine would be slightly negative. So those kind of combined. And you can see that it turns out, okay, of course the hydrogens are slightly positive, the carbon's slightly negative because of that, and the fluorine's also slightly negative. And if we show the molecule dipole, which is, does it have a positive or negative end? Of course, right? The hydrogens are all on one side, or they can be on one side, right? These are all the bottom here, so it'll be slightly positive, and then the top up here will be slightly negative. And so that's, and again, you guys should come and play with this applet and make sure you can see everything. Yeah, alright, let's get something else. Okay, so one thing to remember is, okay, if you have a polar molecule, like water, you can form intermolecular bonds, or a specific type of intermolecular bonds, rather. So if I have some molecules of water, they have slightly negative and slightly positive ends. But we know just from electrostatic attraction, the slightly positive hydrogen and the slightly negative oxygen will attract each other. These are called hydrogen bonds, and these are actually really important for water. And this is what makes water require so much energy to heat up and stuff like that. It's because there's also these intermolecular bonds that hold water together. If we think about the kind of common adage of water doesn't mix with oil, we should think about the energy of that. So why would that be? Well, oil must be a nonpolar molecule, and water must be, well, water is a polar molecule. And energetically, each water molecule will be more stable or have lower energy if it's surrounded by other water molecules, because it can form these intermolecular bonds. So if you mix oil and water, any water molecule that's surrounded by oil molecules will have a higher energy. So once it kind of finds itself around water molecules, it'll tend to stay there. And that's why the oil and the water will separate. And so then the general rule is that polar molecules will dissolve other polar molecules, and also ionic solids as well. And nonpolar molecules will dissolve nonpolar molecules. And again, you just think about the energetics there. Here is, just to remind you, a model of salt, sodium chloride, and just remember that it's an ionic solid because that minimizes their energy, right? Each ion gets surrounded by ions of the opposite charge. Now if I put that in water, now there's a couple things going on here, and we'll only talk about one aspect, but these ions can just break apart and get surrounded by water molecules. And sometimes this is energetically favorable, or favorable for other reasons, and they'll just get surrounded. And you can see that a negative thing would be surrounded by the positive ends of the hydrogens. And same with sugar, and that means that the sugar must be a polar molecule.